Okay. So I guess first, everyone see the screen? Everyone hear me? Okay, excellent. All right, so today, just going to go through the Fabric router pieces, talk about the forwarder, talk about, most of the time's probably spent on xgress, both the external APIs and the internal implementation, talk a little bit about link management, and then we'll see if any other topics come up related to metrics or to routers, like the way the metrics are collected and forwarded, things like that. I couldn't think of anything off the top of my head as I was making the list, but we may sort of, spelunking through the code, things may come up that we want to cover. This is an hour and a half scheduled for the meeting. If we get through all the router stuff, which I wouldn't be surprised if we do, considering how well it went yesterday, then can either stop early, or the other two things I wanted to cover were debugging and sort of future work. So taking a walk through how you can introspect the system, how you can look for bugs, how you can get insight into various performance things or deadlocks or other things that you might need to do as you're trying to find problems. And then, there's a lot of things to discuss in terms of what work is kind of in the near-term future. Okay, so the router lives in the Fabric project as well. So in the Fabric project, we've got our controller directory with all the controller stuff in it, and the router directory with all the router stuff in it. Sort of the as a router, the primary functionality of what the router does is routing things, right? So it has some data and that has come into it either externally or from another router across the link, and it needs to send it somewhere. So there's let me put a note in here. The control stuff was another thing I wanted to cover. So let me put a note in here for that. So probably the I think protocol is probably important. So payloads, acts, and control. Okay. So in general, we're sending data through the routers, and so that's represented by a payload instance. So that's mostly just data, but it's also got, you can attach some headers to it. There's a sequence number for ordering, and there's the header also has the circuit ID that this is associated with, some flags for things like that we're starting the circuit or that we're stopping the circuit, and there's some sort of protocol information about like buffer sizes that get sent back and forth between the two sides, so that we can react appropriately. Buffer sizes, round trip times, things like that the xgress implementation takes into account when it's sending data, right? How much data should I be sending? Do I have to wait before I send more data? How long should I expect to wait before I get an acknowledgement for submitted data I sent, all that kind of stuff. So the three things that we're sending are payloads, acknowledgements. Acknowledgement is again got the header with the information that we're sending around, and then it's just a series of sequence numbers. And I think right now we're just sending individual sequence numbers. Right, so you would send a payload, and the payload is received. You respond with an ACK, and right now there's only going to be a single sequence number, so sequence number per an ACK per payload received. That's another area that we could look at for optimizing at some point. And the final thing is control messages. This is a relatively new addition. So you can do sort of ICMP type things where you can send a control message through the Fabric, and you can say, I want to I want this message to go this far, this many hops before it returns. And it'll then, once it gets to the final hop, it'll send back a response. So you can either, you can kind of do kind of a trace route type thing that way, right? So you can, start with one hop, or start with a large number of hops, and you either work your way up or work your way down, and you can see kind of where there might be latency or problems in the system that way. This is a relatively new bit of functionality. Hasn't been used a lot, hasn't been tested that much, so it remains to be seen like how useful this is, and whether we need to iterate on it to make it better. So yeah, the forwarder is kind of the heart of the router, in that it's just basically a bunch of routing information, right? So we know what circuits we have and what the destinations are for those circuits. A destination could be a link, or it could be an xgress instance, and we'll dive deeper into what that means. But basically, it might be, you might be sending things to another router, or you might be the final recipient, right? So the router might have some connection to something outside of the fabric, and that would be represented by an xgress instance. And the name xgress comes from, it covers both ingress and egress. So the X just means it can stand for both. Yeah, so the forwarder, you give it payloads, you give it acknowledgements, you give it control messages. All those things have circuit IDs on them. It looks up what the destination is based on the circuit ID, and then forwards it. And that might be, again, in process, or it might be writing it to a link somewhere. So let's dive a little deeper into xgress. So there's kind of two pieces of xgress. There is the, and these maybe should be split up, but there's sort of the external implementation of xgress. So that there, the responsibility is getting data into and out of the fabric mesh. So if we take a look at, so let's say we've got a mesh here, right? So we've got some edge routers, we've got some transit routers. When something connects to a router that from externally, right, it needs to get data into the mesh, it needs to get data out the mesh. The fabric doesn't really care how you do it specifically. It could be an in-process thing. It could be talking to an external connection. You just have to provide it the right APIs and provide it a way to get data in and get data out, and it will then just work with that. So those APIs, let's see. So for factory. So if you can register an xgress factory with the router, there's a bunch of them that we have. So we have ones that just are built around the transport library. I'll take a look at one of those implementations because those are pretty small. Even simpler are the proxies, right? So if you just want to kind of proxy a connection through the mesh, you can do that. And then we have the edge and edge tunnel, right? And those add the edge functionality on top of the mesh. So there's a whole bunch of different ways to get data in and out, and generally it comes down to configuration, right? So if you're using the edge, you generally don't want other ways of getting data in and out. Because you want to enforce edge policies. You don't want to provide a proxy where someone can just connect to the mesh and bypass all that. So if we take a look at an example config here, look at the edge router. So there's two sections here, dialers and listeners. So each of these has a way you specify a binding. So that's but just a name for how the xgress type is registered. So we have dialers here that can dial UDP and a transport one, so that the transport one supports a variety of different mechanisms, but that would support like being able to dial a TCP address or a TLS address or quick address or whatever else is supported by the transport framework. And then for listeners, we have Edge, right? So that's going to set up an Edge listener with that the Edge SDK clients can connect to. In this case, we also have a transport address, so that will let someone connect via the via just a regular connection, but it does require you to send a kind of header ahead of time with what service you want to talk to. So this is a little bit still abstract here at this point. So maybe I think going through a specific example might be good, right? So let's take a look at the proxy instance. So you've got a factory, and that factory has listeners and dialers. So let's take a look at proxy. Let's see. Here we go. Xgress proxy. So on the proxy side, it doesn't support dialing. It will. It's only letting you proxy a connection for data coming in. So you can create listeners for it, and the assumption is that you're proxying connections for a specific service. So in the config for it, if we wanted to set up a proxy connection into the mesh, we would do something like binding proxy, and then we'd have options, and we'd have a service, and let's say for proxying, say, an SSH service, we would have this here. And I think you probably also need to specify like a host and port. So the actual listener instance here, yeah, so it takes an address. Oh, right, that's a standard option here. So the address would be something like TCP localhost, say port 1022 or something like that. So a router with this config would have would open a listening socket at port 1022, and if a connection was made to that socket, it would establish a connection, and it would anytime a connection was made to it, it would create a circuit to the SSH service. So that takes care of sort of one side of the circuit, right? This router here would now have a listening socket on the one side that someone could connect to, that would try to create a circuit to the SSH service. The other side is still kind of vague at this point, right? Yeah, you can get into there, you can make try to make a circuit, but still need to define how we'd be able to get out to some theoretical SSH service sitting out here. So actually, let's take a look at that real quick too. So this it's not a ton of code for the listener. It's using the transport library to create a listening socket. Whenever we get a new connection coming in, we use this xgress create circuit functionality, which, look at that is creating a circuit request protobuf message and sending that across the control channel to the controller, which then establishes the circuit. And once you've got the circuit established, it creates an xgress instance here. So that's the other side that we're going to dig into more in a little bit, which is there's the side of how do you get data from outside the mesh into the mesh, and then there's the piece that's handling the ends of that, right? So here, if we take this as an example, or for someone with, so we've got something like this, where we've got an application on both sides. Let's say we're going from this edge router here to this edge router here. There's a terminator here, and the initiating connection is here. There's something that needs to take data, get data from this incoming connection, and send it out. The forwarder will take care of sending it where it needs to go. And then there's something that needs to receive that data and forward it on to the connection on the other side. So, right, we have our payloads that are flowing across the mesh here. Those payloads may change routes over time, but the starting and ending routers will always be the same. So however they get there, when the receiving side receives something, it'll send an ACK back, and that ACK gets routed the same way that the payloads do. There's forwarding tables, so those ACKs get sent back the same way. And if an ACK isn't received in time, we need to retransmit it, right? We need to make sure that we don't have too much data outstanding before we start waiting for ACKs to come back. All that stuff is handled by xgress as well, but it's sort of the xgress on the inside boundary of the fabric rather than on the outside boundary of the mesh fabric. Okay, so let's take a look at the other side. So this is the xgress proxy is a good example of an xgress factory with a listener that can take data in. If you try to create a dialer with it, it will throw an error and say it's not implemented. So let's take a look at xgress transport. Here, this factory can create listeners and dialers. So the dialer API here is very simple. It has two things: a dial and is terminator valid. So the dial is given a destination, a circuit ID, an address, a bind handler, and a logging context. So this is used when on the other side, right? So when we have a terminator, let's take a look at that again. I have a good example here. Not so much. Okay, so I've got a running ZT controller, ZT edge router here. So if we take a look, I don't think there's any services right now, right? So we could do, create a service, SSH, for example. So we've got our SSH service now. We need a terminator for it. We're going to have it hosted on edge router 1 for the SSH service. And let's say we want it to dial out to a locally hosted SSH instance on port 22. And then we give it a binding, so that could be transport. Oh, the name of the router wrong. There we go. So now if we list terminators, we'll see we've got a terminator for the service. It's this address and this binding. So the binding tells the router what xgress type to use, right? So we have those bindings in the config file here, right? These bindings here, these names match up to the names that are defined in the terminators, right? So, and they're also match up to the names that we register these with, right? So if we look at where this, say, the transport factory is registered, right? It's registered with some registry here with the name transport, right? So that kind of ties all these things together. So when we, when our smart routing finishes and we have determined that we're going to end up using this this particular terminator, the information about the binding and the associated address gets sent to the the router, right? So if we take a look at the route handler in the router, so this is the handler for the control channel that receives route messages. So a route message has a circuit ID, some forwarding information depending upon if it's doing things in the middle of the route or at the end of the route. It's going to have forwarding information, but it also might have this egress, right? And the egress tells it the binding, the address, the destination, and some pure data. Pure data is used for things like setting up end-to-end encryption. So if we take a look at how that's used, so if we have egress, then we know we need to dial that. So we first check to see if the forward already has a destination for the address. If it does, then we don't redial it. Otherwise, we try to connect this egress here. So we'll find the factory for that binding. We'll create a dialer for it, and then we will call dial with the destination and the circuit ID and the address. So in the case of xgress transport, our dialer will parse the address, dial it using the transport framework, and if it succeeds, we get back a connection, and we'll set up a new xgress instance to handle the terminating side of the xgress connection. All right, so that's how that's kind of the outside of how we get data, into and out of the fabric, right? We've got our factories that can do different things depending upon, if we want to talk to an edge SDK or talk to a raw socket connection, or, another thing that we have is we have a tunneler. The tunneler can be run directly in the context of the router. So in that case, where our dialer and our listener are talking to the tunneler, the local tunneler instance, rather than making connections directly, right? So it can be IPC, or not IPC, but intra-process communication. It can be network communication, it could be IPC, it could be whatever. Does that kind of make sense to everybody? I feel like it's a kind of a little bit convoluted, but it's a very it's proven to be relatively powerful, right? In the sense that something like the tunneler, embedding the tunneler in the router turned out to be relatively straightforward. It didn't require any changes to the router or the controller, right? On the router side, we were able to just create a new xgress implementation where the listener side spun up the tunneler, which would then listen for incoming data on a ton or T proxy connection, and the dialer would use the tunneler to make connections out using the tunneler functionality. And then we were able to use the X control framework to kind of seamlessly add some new handlers so that the tunneler could do tunneler specific things on the controller and router sides. This is kind of the natural boundary between the two portions of xgress, right? There's the portion of xgress on the outside that is knows how to get incoming connections and dial things, and then there's the inside of the xgress, which is handling the kind of ends of the fabric mesh connection of the circuit. So that point of connection between those two things is the xgress connection, right? So this is what each type has to implement. So we'll have a for transport, we have an xgress, a transport xgress connection that wraps a transport connection and translates the read payload into a read on the underlying socket and a write payload onto a write onto the underlying socket. For xgress edge, that's a more complicated thing, right? We're talking to the SDK. So instead of writing the data directly to and from the underlying socket, the SDK has a more message-based paradigm where instead of writing just a byte array, it wants to write a message of type data, and because there's other control data that needs to go over the same pipe, right? So that will have a slightly more complicated API. But this is ultimately what each xgress implementation needs to do. So the dialer, when it dials whatever address it's been asked to dial, it gets this peer, which is a transport connection. It takes that peer and wraps it in an xgress connection, and then passes that into the xgress instance, so that it basically has something to read from and write to. And each of the xgress types will have a different one, right? So like there's a xgress transport UDP, right? So there we have to, instead of writing to a stream socket, we're writing UDP datagrams. I think the main thing is for this piece is to kind of see how things are tied together, right? So we've got our config file, which lists our available dialers and listeners. When the router starts up, it knows about what kind of xgress implementations are supported, right? In the pure fabric, it's got the proxy, some proxy implementations, proxy UDP, transport UDP. The edge code adds on to this transport edge transport, which adds end-to-end encryption support to on top of the transport pieces, and xgress edge, which adds support for SDK clients, and xgress edge tunnel, which allows embedding the tunneler directly into the router. And then when we start the router up, any listeners that we have registered, we just go through them. We create a new listener for each of the xgress instances that we have and start that listener up. So we'll have in the example we looked at, there was an xgress edge and an edge and a transport listener. So we'll have two things listening for connections coming in, right? So that side of it is important to understand how you can add a new listener type, or how to see how the listener type gets started. On the other side, the important side, or the important information is when route messages come in, when we're establishing circuits, that this route handler gets called with a new route message. If we check to see if there's an egress portion, if there is, we find the appropriate xgress factory for the binding that were specified in the terminator, and create a dialer for it and dial, and then the underlying xgress implementation will take care of establishing that connection whatever way it might be, right? It might be, usually it's either dialing a socket or finding an existing socket. Like if you have an SDK client that has connected into host to service, that there's already a connection from the SDK client to the router. So we're not dialing a new thing, we're taking that existing socket that exists and creating a new sort of virtualized connection over it. Let's take a look at the inside of xgress then. And this is where the complicated slide comes in. Okay, so to understand kind of how we manage data flowing end to end over the fabric mesh, let's look at an example where we have two routers connected by a link, and each side has a client connection, right? So maybe on this side, this client connection is a SDK, an edge SDK client that has connected in. And on the other side, maybe we've got either a tunneler that's dialed out somewhere to a service, or we've got, using xgress transport, we've dialed out directly to some service. We've got some connection here that we want to send data to. So we have on this 2 xgress instances, and they are symmetric, right? In that data flow works the same in both directions. So we're going to talk through what happens if we want to get data from this from router 1 to router 2, but it would work the same way, just in reverse, if we were sending data from router 2 to router 1. So each xgress instance has a reader go routine called the rxer, which is calling read payload from the client connection. So we read until, and it'll block until it gets something. So now when data is available in the client connection, we'll read it in, and we will push it into the link send buffer. The link send buffer is what's responsible for kind of managing the flow of data. We don't want to read data as quickly as possible from the client connection unless the other side can keep up, right? So we're tracking, we start off with a given sort of window size to say, so maybe like, I forget what the default is, if it's like 4K, something like that, but let's say we start off with a 4K window size or a 64K window size, or some arbitrary size that we start off with. So we'll read data off of the client connection and stick it into the send buffer until the send buffer is full, till it's hit the window size. And all that data is getting sent over the link. But until we start getting ACKs back, at some point we'll have kind of filled the send buffer, we'll hit the window size and we'll stop. This will block, we'll be able to read any more data. So let's say, so we're sending this data through, it goes across the link, and there's a payload ingester on this side that will try to stuff things into a receive buffer on this side. So again, the receive buffer also has sort of a maximum size, and if the receive buffer gets full, we don't want to block, right? Because there's only a single thing reading. This link is a single stream of data. You could have hundreds or thousands or tens of thousands of xgress instances in a given router, all pumping data through this link. So if there's a slow connection on this side, we don't want to block the link from being read, because we don't want one slow connection on this side to stop other fast connections that are maybe here, right? So what happens if the payload ingester can't deposit data in the link receiver is it will drop the payload, and that will then at some point cause the send buffer to notice that it never got an ACK, and it will then resend it. And then, but presumably, in most cases, the data will end up in the link receive buffer, and then similar to the rxer on this side, we have a txer, or a sender on this side that is always trying to take whatever data is available and push it over to the client connection. And it's also responsible for, when data is received, for sending an ACK back across the link to the send buffer. And then when every time the link send buffer gets an ACK, it will say, okay, there's algorithms in there that say, okay, I've gotten X number of successful ACKs in a row, no retransmissions have happened, seems like things are going well, I'm going to increase the window size a bit. And then if we do have to retransmit, then may start shrinking the window size. So we're trying to kind of adapt the window size so that so that's appropriately sized for the rate at which we're able to send data across to the other side. If we do have to retransmit, the link send buffer will push that into, there's a retransmitter, which keeps a queue of data that needs to be sent across the link. If we happen to get an ACK before it gets sent, we'll take it out of the queue. Otherwise, it will get retransmitted, and we might get multiple ACKs for it. If we get an ACK right after we send, we'll make another ACK for it. And let's see, other than that, the link receive buffer is also making sure that our ordering is correct, right? So if we get payload 1, get payload 2, and get up to payload 100 or whatever, and then this is a slow connection, payload 101 is dropped, and then we get payload 100 and 103, 104. We get some that are in advance. The link receive buffer won't start pushing those over to the TXT won't start pushing those over to the client until we have everything that's in order. So until we get payload 101 inserted into the missing gap, we will we'll wait. Some history on xgress. So so I think in 0.17, this was structured somewhat differently. It didn't have the notion of dropping payloads, right? So the reason, in addition, the reason we have retransmission is not just because we may have to drop payloads, but because links may go away, routers in the middle may go away, right? If we get rerouted, we may end up dropping payloads that way rather than dropping them because we have a slow receiver. So the retransmission is important for that reason as well. If path changes, you need to account for the fact that maybe it's a router drop, a router died in the middle of sending your particular payload along. But it didn't have the notion at that point of dropping things because of slow connections. And then I think as part of the 018 work, this was refactored quite a bit. And so Michael was working on the transwarp stuff and had done a ton of work with sort of refining these sorts of algorithms and making this work sort of over a UDP based framework. And so because we were hitting problems with the xgress implementation, I kind of re-implemented a lot of the things that he had figured out for transwarp, but in the context of the existing xgress stuff. So if you look at the transwarp stuff and the xgress code, you'll see that it's doing a lot of the same things. There, as a next phase on the transwarp stuff, Michael then split out the sort of the retransmission pieces into its own API called the Lithium. So we would be able to use it for xgress, and so so you kind of use the same retransmission and flow control logic at different layers, right? Because you might want to use it for a point-to-point link doing UDP traffic. You might want to do it for an end-to-end circuit that's going across multiple hops, right? But the logic is kind of the same. You might want to tune those things differently, and it's all tunable. But the basic algorithms of you want to be able to have windowing, and you want to have both send windows and receive windows, and you want to be able to adjust window sizes based on whether ACKs are successfully received or not, whether you have to do retransmissions, whether you get duplicate ACKs showing that maybe you're retransmitting too aggressively, right? Being able to send TTLs around so that you kind of have a good idea of how soon you should retransmit, because you want to retransmit as soon as possible, but not too soon, because otherwise you're sending duplicate data. All that kind of stuff is pertinent both to point-to-point links as well as whole circuit connections. So that's something that is kind of pending for future work, is to hopefully take that Lithium code and either take it as it is with the other changes that Michael had, or just take the Lithium by itself and integrate it into xgress. So links. So yeah, we're going to move from xgress to links now. This is a relatively constrained topic. So the basic things to know here are links are controlled by or links are mostly managed by the controller, right? So every time a router connects to or disconnects from the controller will take a look and see, do I have as complete a mesh as possible, right? So taking a look at the config file here again, we have a link section here, and that controls whether this router is capable of dialing and or listening for links. Let me see, I think. Okay, yeah, so here's an example of a router configured with a link listener on a specific port, and also for a link dialer. So let's say transit router B here connects to the controller. It's configured with a link listener. It will talk to pretty much, the controller will say, okay, there could be links from A, C, E, and D all to B. So I'm going to ask that to happen. I'm going to go out and send them a dial message to each of these routers and tell them to connect to B. There'll be then a pending link created for each of those that won't be used for routing yet. If each of those routers, when each of those routers connects or fails to connect, it will send either a link fault if it fails, or a link connected message to the controller. The link connected message is received, that link is now marked as connected or active, or I forgot the verb or the state is there, but it will then that link can be used for routing purposes. If a router notices that a link is broken, right? So it tries to write to a link or read from a link and gets an error, it will notify the controller of a failed link. That link will then be marked as gone. At some point in the future, it'll notice that we don't have a link there anymore, and we'll send another dials to reestablish that link. Again, as we talked about yesterday, links are currently stored in memory only. So anytime the controller went down, it would forget that all of these links existed and reestablish another mesh. So all these routers would end up with usually the same kinds of links they already had, just another set. The old links would not get used anymore. They would still exist, but they wouldn't be used anymore. The work I'm working on now fixes that by each router now has a link registry, and when you ask it to dial, it will check the registry first and say, do I already have a link to this router with this address? And if so, it will respond back with the link information that it already has, allowing the controller to then kind of reestablish that information, so we don't end up with duplicates. So that should help. There's also, there was also a case where if you have a lot of routers trying to establish a lot of links, right? Because if you've got a fully connected mesh, right, each router could be connecting to almost every other router if they're not behind a firewall. So it could take a while for those links to get established. If it's dialing a whole bunch at a time, it might get a flood of, say, 50 or 75 dial messages, and it's then got to dial, and there's a pool. So those won't happen all. To some extent, that'll happen concurrently, but they're it's pooled, so it'll do a chunk at a time, kind of. So the controller might get impatient and say, I asked you to establish a link, but it hasn't happened yet, so let's try again. And you might get some duplicate links that way. I did some work to try to mitigate that to some extent by adding a pending time on the link. So if you don't get a link, it gives it a chance to try to establish that for a little bit longer. So if it sees it's got a pending one and it hasn't hit its timeout yet, it will wait before trying to establish a new one. I think
there are also sort of duplicate links or dual links now between, like, for example, when it's setting up the fabric, B will dial C and C will dial B. So you end up with two links, or has that been fixed?
Yes. So if you have listeners, it will do things in both directions, right? So if B and C both have a link listener, then it will tell them to dial in both directions. And the reason it does that is because it's possible that there's a firewall in the middle there, and maybe one direction works but the other direction doesn't, and the controller doesn't know that. So it'll do its best to kind of tell it to do everything, and then if something doesn't work, as long as one direction works, it's okay. The work I've done so far doesn't really address that. It should limit it to 2, right? So you should have at most 2 links between any given set of routers. But it doesn't take care of that one extra duplicate that can happen. I'm not sure it's worth it. It might be. It can cut down, if you've got a pretty fully connected mesh, you can cut the number of links in half, which can cut the routing time by quite a bit, right? Because it's many fewer links it needs to traverse. But I think that's probably some follow-up work to look for duplicates and maybe eliminate them, right? So if you have, one of the things I added was now when A dials B, it sends along some information about itself, right? So B knows that the router on the other side is A of a given link now. So it can, now that we've got a registry, it could go through and look for duplicates and eliminate them. We'll just need to be careful as we add support for multiple types of links, that we again don't remove things that we shouldn't, right? Like if say you've got like a UDP link versus a TLS link, or like a cellular link versus a wired link, we need to make sure that type information gets propagated so we can distinguish between them. So it's not just like, if you want to have 2 links of 2 different types between a set of routers, that we make sure that is part of the identity of the link or part of the metadata of the link, so that we can distinguish between those and make sure we have a unique set of links. Make sense?
For sure.
Okay. Okay, I think that might be. Oh, yeah. I guess I don't know that. So we have peak handlers. So yes, we talk about channels and peak handlers. So all the links have peak handlers defined, and they collect data about every time you send a message over a link, it gets tracked. You see, I think probably, yeah, the only thing that's kind of maybe a little more interesting here, so most of this is sort of regular standard metric stuff, right? We've got a bunch of meters, right? So we're tracking how many bytes, how many messages we're sending for the application as a whole versus how many we're sending for this particular link. And that's pretty normal. The only more interesting thing here is maybe the usage counters, right? So we have a notion of a usage counter, which whenever we send data, look where this is used. So whenever we receive a message here, if it's a payload, we update the usage counter for the payload circuit ID with the size of the data. So what that does is internally it's creating buckets. So it will say, okay, within this minute, I've got a bucket for this circuit, and I'm gonna update it by this amount. And then when the bucket rolls over, we start accumulating a new set of data for that minute. And completed buckets then get shipped up to the controller and then outputted as events. So if you've got 100 different circuits on a router, we'll have 100 buckets per minute, and then they kind of get flushed as they get filled, right? So as the minute expires, those buckets can then be shipped up to the controller and emitted into an events log, which then gets pulled into the processing. Yeah.
So that can be a lot of data if you're talking about a big network with a lot of routers.
Yeah. I mean, that's certainly why why it gets we bucket by the minute rather than something smaller. It could certainly also end up being a lot of overhead on the control channel and certainly a lot of events. But I mean, that's kind of the granularity that most people want, right? They want to be able to say, they want to be able to take that data and say, okay, this identity was using this much data on this service at this time, right? Or and then because the data is being accumulated per circuit, it lets you roll things up a whole bunch of different ways, right? That circuit is tied to an edge session, which is tied to both a service and an API session, which is then tied to an identity. So you can say, yeah, I want to see how much traffic is being pushed over this service in this time frame. I want to see how much data is being used by this identity or some combination of the two. That's kind of the granularity at which we want that data. So far, it hasn't been a problem, but it's certainly probably, I would assume it's the biggest source of, the biggest contributor to data in Elastic, if I had to guess. I don't know if, I think Mike was on yesterday, I don't think he's on today.
Yeah, I'm sure it's easily the biggest index we have, or set of indexes.
Yeah. If it's not, I would be surprised.
I have one question about peak handlers. Can they change the data, or are they purely observational?
They can change the data, but they're not supposed to. So there's nothing, they could reach into messages and change them. Although I think they get invoked after send, so you could change it, but it wouldn't make it onto the wire. There is, however, a different API here, the transform handler, which gets invoked before we send and before we hand it off to the receiver. And I think Andrew's using that for, is there going to use that for something? I think for the to add a header for the controller move bits in the SDK. I think that's probably the only use of that so far.
No, I took a different path. I added the settings message that can be sent down on Router Connect.
Gotcha.
In preparation of sending any kind of setting down, should we need to do it in the future.
Makes sense.
But I did look at using those, and my first implementation did use that. But then I had to deal with situations where what happens if you receive two messages with the header in it, and the header just appeared magically, and for some reason there's like a file lock on writing the config file that temporarily causes two messages that both have the header at the same time. Then I have to synchronize around it, and I was like, this is more complicated than it needs to be.
Gotcha. Yeah, I don't think we have anything that uses the transform handler right now. I mean, technically peak. Yeah, that's good.
I used it for like a hot minute.
Yeah, I think. I mean, I don't think we need to take them out because I think there's not really not much overhead if you don't have one defined. But yeah, they haven't been used by anything so far.
Yeah, I could see maybe one every 1,000 messages gets a trace header or something in the future to kind of get some random latency scattered through, things like that.
Yeah, and I have been thinking about for router links. Right now, one thing I want to make sure of is now that the routers have a little more control over their own links, making sure that we don't end up in a case where like one side of a link thinks it's okay, and the other side thinks it's dead, and then the side that thinks it's dead says, "Oh, my link is dead. I'm going to let the controller know." The controller says, "Oh, I'm going to recreate this link." Sends a message to the router on the other side, and then that one says, "Oh no, I'm good. I already have a link," and sends back the link that isn't working on both sides. So, making sure that we have health checks kind of or heartbeats. Currently we're sending latency messages every so often, but it might make some sense to put some additional information on link messages. Every so often pop a header on there that so that we get things sort of in line consistently. Latency messages can get lost in a storm of data messages sometimes. So if we just pop things into the flow, then we're less likely to be a problem. So the transform handler might be a reasonable way to do that. We also use peak handlers for tracing. So one thing you can do is you can use the inspect or ZT Fabric trace, and you can tell it that you want to see messages that are flowing across links or control channels, and the pecan will kind of grab those and forward them back up to you, and you can do some traffic debugging that way, which is kind of neat. One other thing on the links that I forgot about that I wanted to mention was that we have 2 link implementations. So there's a xlink API. So this is the new registry. Lets you get dial locks and let you know whether you've dial succeeded or failed, and will return an existing link if there's one already there for a given dial attempt. But the xlink implementation itself, has send methods for each of the types that we want to send across it, as well as what router it's connected to. And we have 2 implementations. There's a standard one with a single channel where we send everything across the same channel, and there's a split link implementation where we have a payload channel and an ACK channel. And payloads get sent across one channel, and ACKs get sent on another one. And that's an attempt to make sure that we're sort of prioritizing or making sure that ACKs aren't getting held up by data. I think we need to do some more testing on that to see if it's worth the complexity. I saw some benefit when I was testing this, a year ago or so, but it would be worth, I think, revisiting. And especially in the context of if we rework some of the underlay pieces, looking at UDP links and maybe looking at incorporating the lithium bits, then definitely need to retest this. Because if you're using UDP underlay, then just kind of spraying things out there. Having separate links for UDP probably doesn't make any sense.
Is there any attempt to detect when a link maybe gets a bad route? So you go and dial another fabric and it goes through a network device that's having trouble, or picks a slower backbone somewhere, and not the main backbone, but a more of a side channel.
Not really. So I guess we account for that a little bit in the fabric itself, right? So if there's a bad link between 2 routers and there's an alternate route, then generally that route will perform better and have better latency, and we'll prefer it. But we don't really do anything like trying to other than our latency checks, we don't look at the health of that. I guess the tricky part there would be like figuring out, is this link functional but not measure up to our expected measures of success, right? Like, is this link slower than we would expect it to be for whatever reason? That'd be an interesting thing to think about. I'm not sure. Maybe you'd have to define, like, if we had link rules for, say, setting costs and things like that. Maybe you could have link rules that say, this link should be able to support this bandwidth, or here's some set of metrics that we would expect this link to be able to sustain. If it doesn't do that, then raise an alert or retry it, or both, or something. I don't know.
Maybe now that there's a metric or registry of links in the router, maybe it can know historically a little bit since it's been up or something.
Yeah, I guess it could. Yeah, I have to think about that to see. It's an interesting thought, though.
Yeah, I just wondered if there was some way to try to detect a degradation, and I think probably the fact that it will just stop using that link is good enough.
Yeah, maybe. Yeah, I mean, when you brought it up, it reminded me of like when you are spinning up like an EC2 instance, right? Sometimes you get EC2 instances that don't behave as well as other ones, right? They may have either they may be degraded in some way, or they're really busy because somebody else is using them. So you might want to try a different one. And there's probably kind of ways you could, do health checks on it over time to say, here's if I run this CPU intensive task, it finishes in this amount of time. So you can kind of quantify that a little bit.
Maybe have some off hours where you do a transfer test or something, for the network. Yeah,
it'd be interesting, I guess, to have some measure of what you would of what you kind of expect the system to be able to do. Like when you set something up, if you were to like bring up a new router to do a quick bandwidth test on it before you use it, or I don't know. I guess the question is how you set that level of expectation. I think some debugging bits. One of the first things is stack dumps. So you can get a stack dump in a Go native way by calling kill3 on a router, which will, or on a Go application, which will I think just kill it generally.
Yeah, that's a Linux and Mac OS thingy as well. It doesn't work on Windows if you happen to ever have to do that.
Okay, good to know. So that's one way to do it. Another way is with ZD, do ZDPS stack ZD router, and that will reach out via. So there's a little agent running inside the controller in the router, which is listening on a Unix socket, and it can find it by process name. So if there's multiple ZD routers, then you have to give the PID, but you can just also give it the process name. There's only a single one, so you can do ZD controller and ZD router, and then we can split these into the temp file. So like controller stack and router stack. And then there's I generally use, there's a tool called Go Routine Analyzer. Which is unfortunately written in Java, which has caused Andrew to go build his own tool because he hates Java so much.
I refuse to install that security vulnerability mess of hotness anywhere on any system I own.
I saw that last week when you posted that to private, and I thought, geez, I thought we already had this, but then I just let it go, and now it makes sense.
Yeah, I did look at running it in Go because I was, was trying to get all in on Go. Wait, did I do the same one? I don't know. So this has tools for splitting things. That's weird if they were. No, they are different, I think. Yeah, they both happen to have 87 Go routines, which is kind of strange. So you can split the stack up into by things that are basically duplicated, right? So it'll find, even though these are not exactly the same, right? They only have different memory addresses, but the stack itself, minus the Go routine ID and potentially different addresses in here will be the same. So it lets you see usually pretty quickly if there's something where the bulk of the work is, if there's something stuck, or if there's a huge number of connections or whatever else. You can kind of tell that pretty quickly by doing that. And then it's also used to be able to see what the individual things are. You can kind of go through and take a look at if you're looking, for example, for something that's got a lock, you may have a whole bunch of Go routines stacked up on a lock, and then the thing that actually has the lock will be different than the rest, so that you can find that one in the unique ones. You can also do filters, so you can find all the bolt stuff that's running with a regex. Right now, there's only one thing. Yeah, it's see, there's probably, I think these are the ones I was looking at last. Stack. Yeah, so here's one that's got a few more Go routines in it, just a couple. So here you can see right away, there's a whole bunch of things trying to get a specific, they're all locked on bolt basically, right? And then from there you could create a bolt filter. And then from there, what can be useful is that you can, I shouldn't have opened that up. You can extract the duplicated from here. And then this shows you just the unique ones that are left, which can be useful. Kind of helps you really quickly narrow down what you want to dig into.
Does that search only does it search the entire go routine stack trace, or is it only the top one?
The whole thing.
I guess the whole thing. I guess it would have to be the whole thing, because if it's on semiquire mutex, the second one would be bolt. All right.
Yeah. I think that's mostly it for the go routine stuff. Oh, actually, there's one other thing, which is you can so also check out Andrew's thing. It does, I think, similar things in terms of being able to do the grouping of similar stack routines.
It creates stack signatures like very similar to yours. It doesn't do the searching that yours does. And it's also a single UI window, because it's my first Go UI, and it's my first immediate mode GUI. And it was very confusing to even just get the one window going. So I called it a day, and that was 1.0. So
yes, that's why I did it in Java, because I've done Java GUIs before, and I needed the functionality. I didn't want to learn something new with them. I just wanted to get the thing done. But hopefully you will take the pain, and then eventually yours will be awesome, and then we can use that.
I'm hoping somebody will start contributing to it. It's just out there in GitHub. I don't know if anyone's ever going to find it, but
yeah,
we'll see.
Right. So the other thing you can do is, if you're trying to debug like a customer setup, or if you're trying to debug, something like if you're doing testing. I've done testing like in AWS, where you've got a whole bunch of routers out there that you want to do stuff with, and you don't want to like have to SSH to each box individually. One thing you can do is ZD inspect, I think. No, ZD fabric inspect. So you can look for, you can give it a set of basically which processes you want to get. So the controller has an ID, each router has an ID, so you can give it a regex for which IDs you care about. And then I think it's just stack dumps. Stack, oh. Stack dump. There we go. So you can see results 2, and it's got control client stack dump, and then that's the router ID there, dot stack dump. So you can spit that. You can spit that out to a file. And then you can use ZDops. Split stack dumps. So now we've got a dump file for the controller and one for the router. And then you can inspect those as usual. So that's been useful. Like if, when I was doing work in performance category performance analysis, and I had a whole bunch of not just routers, but also, SIMs and things like that, where I was trying to track down deadlocks in various places. So being able to get all that in one go, split it all up, pull it all into the analyzer, and go through it there was very useful. Currently, the only thing you can get using zfabric inspect is a stack dump. It might be useful to be able to grab other things, but that's the only thing right now. If you are local to the box, you can also, so there's other things you can do with ZDPS. So you can do GC, ZD router. Oh, did that just run GC? I guess it just runs GC. You can get some memstats. You can do a pprof. That's something flip this out to the router growth. Growth. This is going to take 30 seconds because it's going to run the profile for 30 seconds. So you're getting, you know, a 30-second slice of a life in the day of the router, or a day, 30 seconds in the life of the router. And then it'll spit it out. You can also get a heap dump, which will, I think that just gives you an instant setting change. So then if you want to look at this, you can do go tool, pro, web, ZD router, and that will spin up. Oh, but yeah, the problem is that the router is not actually doing anything right now. So it's because it's so busy, there's nothing there. But if it were busy, there we go. There we go. If it were busy, there'd be some stuff here, but there's not. So there's nothing to see.
All of the dumps, the pprof dumps for memory and CPU, as well as the go routine stack traces, when you issue those commands, those are actually going out over the control channel, right?
No, they're going over the Unix sockets to. So the stack dump one, if you're using ZD Fabric Inspect, that goes over the control channel. If you're using ZDPS, that's going directly to the Unix socket and direct to the application out of the control channel.
I meant when so it only works with locally resident running processes. It doesn't work across the entire network. Like, so you can't from the controller just say, get me all the dumps across all the routers, right?
Correct. We could add that, like the same as we have the inspect support for stack dumps. We could add the same thing for heap dumps and CPU profiling. The problem with that is that it might not be that useful. One, it's it's a lot of data sent over the control channel. Although I'm not super worried about that. If you're doing that, the network is usually impacted anyway. So what's a little bit of extra impact at that point?
Yeah, I was thinking, what happens if the control channel's already clogged up? Like, that's the problem. Like, you can't.
Yeah, the bigger problem is that you may have a router that's unresponsive, right? It may still respond to the IPC, but it may not be responding to the control channel. And a lot of times that's what you're trying to debug, is like, why is this thing not responding anymore, right? So that's why this is the the most important way to be able to do it. You can do log level changes. So like right now, this is the router is running in debug mode, or it's at info level. So you can do set log level, debug, ZD router. Actually, I got that order wrong there. Yeah. Set log level on ZD router to debug. And then there's only some time in the next little bit, something will fire here to say. Oh, it actually did spit out a message saying set to from info to debug. Set to. Oh, there. So there's a debug message now that we didn't see before. And you can also do you can set channel log level. So the one thing to look into is the logging framework has channels, so you can kind of it's somewhat similar to the way in Java, like you can say I want to set the log level for this class to, or this logger to this level. Here you can, when you do some logging, it may have a channel defined on it, right? So we have a few channels, not a bunch, but if you look at the routing, for example, routes. So here, yeah. So we have a channel logger with a log context of established path. So you can, instead of turning the whole router up to debug, you can set just the established path to debug. So that way, if you're interested in some more targeted logging, you can do that. And then finally, just for testing and debugging purposes, you can get some debugging information out of the router. You can do dump routes. Probably have to do this still. Yeah. Oh, no. Router, oh, dump routes. PD router. Oh, I don't have any routes, so I don't have anything running over it yet. I don't have any API sessions either. Probably not worth setting those up right now, but you can, if you want to see what the router knows about, you can do that. You can also add a route if you want to mess with it. You can, for testing and debugging purposes. And you can also disconnect and reconnect the control channel, again, usually for if you want to see how it reacts, right? If you want to simulate the network going down between the router and the controller, you can tell it to disconnect and reconnect. Then I'll set up one more meeting to talk about sort of future stuff. And that's it. Thanks everybody for your attention, and talk to you later.
Thanks, Paul.
Sure thing.
Enjoy your latte.
Thanks.